Hello, good morning.
Good morning.
Hello, can you hear me?
Yep.
Yep.
Okay, I bought a new mic, a nice mic, and I'm testing it out today. So do you hear me better with this new mic? Before my mic is in my earphone here. Do you hear me better? Or is it the same?
Sounds good. I don't know how different it is, but it sounds good.
Okay, I can't hear you though. That's strange. I saw David speaking, but I can't hear you. Can you speak again? Oh, your mic is mute, David.
No, it wasn't muted.
His mic wasn't muted.
Yeah, your mic is unmuted and yet I cannot hear you. Can you speak again, David?
Hello, testing.
Well, I can't hear anything from you.
Is your volume up? Can you hear now?
I can't hear David speaking. I don't know why. Let me see what could possibly be wrong. Michael, can you try to speak? Can you unmute yourself and try to speak?
Can you hear me? I'm talking now.
Are you
How about now?
speaking?
Yes, I'm speaking.
Can you hear Michael?
Yep.
I can't hear him though.
Yes, I'm
What is the
speaking.
problem
Can you hear
then?
me?
Let me unplug my thing. Can you speak again, please?
Yeah, I'm talking right now. But
Okay, I didn't hear anything. So what is the problem then?
New mic.
Well, I don't know what the problem is. Does this mean that when I use the mic, I cannot hear you? Let me unplug the mic.
Can you hear now?
Yeah, I can hear you now.
Okay. We could hear each other, so it's on your side.
So when I plug in the mic, the fancy mic that I have just bought, I cannot hear you.
There's probably a setting on your computer where you can select the input devices. So you might just need to play around with that. We can hear you fine like this, so if it's...
Okay, I'll do it next time then. I just not use the mic at this point and just use the mic from my microphone. There's a small mic here, but it doesn't work very well. Can one of you speak and see if I can hear you?
Can you hear?
Yeah, I can hear you. Good.
Okay. Yeah. Your audio sounds fine for us so far.
Okay, let me get started then. Because let me get started. And I share my screen. And my topic today would be on the quality factor of a cavity, and then followed by mode orthogonality. These are interesting topics. Okay, so let's start with studying the quality factor of a resonator or a cavity. And we can take the simplest cavity or resonator that we can think of, which is indicated by an LC tank circuit. So if you were to drive an LC tank circuit with a voltage source, you will find that, well, there will be an impedance. And of course, most of us know how to work out this impedance. The impedance Z is given by J omega L plus 1 over J omega C. Okay. And the thing about this impedance is that one of them is positive, the other one is negative because of 1 over j omega. So you can actually write this as j omega L over 1 omega C. You can see that these two terms can cancel each other if you select the frequency to be omega equal to 1 over square root of LC, and the impedance is 0. And when the impedance is 0, what it means is that you can take away the voltage source. Okay? The voltage source can be set to 0 because the current is given by the voltage divided by the impedance, or equal to voltage times the admittance. Okay, and when the admittance is 0, which is this case over here, the admittance is infinite, sorry. When the impedance is 0, the admittance becomes infinitely large, which means that you can have a 0 voltage, and yet I is not equal to 0, because 0 times infinity, 0 times infinity is undefined, essentially. Then I can be anything that you choose to have. And yet there is a solution to this equation. So when we hit the resonance of this circuit, Z becomes infinite, Z becomes 0, Y becomes infinite, then I can be a finite value, and then I would be the current that flows back and forth in this LC tank circuit. However, if you have a little bit of loss in this LC tank circuit, then you know that the impedance now, Z is j omega L plus R plus 1 over j omega C. And then you can actually work out the admittance. The admittance is actually the inverse of this. Okay, you find that these two terms can never exactly cancel each other. If omega is real, this thing cannot go to 0. Okay, you can convince yourself of that quite easily, which means that Z is never 0, which means that the admittance is never identically 0. And that means that if you were to turn off the source, okay, there would be a current, but the current is not oscillating forever. The current that we have in this left-hand circuit will keep oscillating and oscillating and oscillating forever. Okay, because there's no loss. But the one on the right-hand side, because of the small resistor, the current will become smaller and smaller. And that is when we have a loss in a LC tank circuit. And how does this translate to some real-life applications? You will see that when you observe the voltage in the LC tank circuit, it would diminish to 0 with respect to time because of the loss, the loss present. Okay, when loss is present, then the voltage has to decay in the solution, and we can actually relate the Q, the definition of the Q of a system, to this decay rate and the oscillations and so on. And so the way to define a Q is that Q is number of cycles per let me see. I should say the number of cycles here. Say if I look at this picture, when the loss is present, if you start out with the value of 1, then after a certain time, it will decay to e to the minus 1 when t equals to tau. So this thing would decay like t over tau, when t equals tau, okay, the value decays to 1 over e. Okay, the time constant tau is defined to be the time it takes for the decay or the signal to decay to 1 over e of its original value. You can call this the time constant, and the Q is defined to the number of cycles within the time constant. Okay, so if the time constant is tau, then what you have is that let me see. Let me see how I should define this. Okay, I should think of this that the voltage, the energy, which is the voltage square, if the voltage goes as e to the minus t over tau, the current will also go as e to the minus t over tau. The power, the energy, which is proportional to either v square, which is proportional to I square, would be proportional to e to the minus 2t over tau. Okay, it will decay with twice the rate. And then when t equals to tau over 2, let me see. So the number of cycles within this time constant is given by omega. Okay, Q will be equal to omega times 2 over tau, because 2 over tau is this interval, the interval before the signal decays to 1 over e. This is 2 over tau. And if we count the number of cycles within this interval, that is the Q of the system, which means that if tau is very large, that means that it takes a long time for the signal to decay to 1 over e of its original value. Then there will be many, many cycles before you see that it decays to 1 over e. So Q is counted as this number, and then you can actually write Q in another way, which is that you can define the decay constant, that this thing decays as e to the minus 2 alpha t, and then alpha would be 1 over tau. Okay, alpha is the decay constant. Then Q can also be written in terms of alpha. It would be 2. Let me see. Did I get this right? Q should be equal to omega over 2 alpha. That's what I'm trying to get at. And then when t equals to when t equals to 1 over 2 alpha, then e to the minus 2 alpha t becomes 1 over e. Okay, so the time constant tau should be equal to the time constant tau, hence should be equal to 1 over 2 alpha. So that is wrong, isn't it? The time constant here should be 1 over 2 alpha. So tau should be, so 2 alpha is 1 over tau. Okay, so I got myself confused. So it depends on whether you are looking at the voltage or the current. If you're looking at the voltage or the current, then the time constant should be defined to be this, and then you can get your tau to be 1/2 alpha, and then your Q would be omega/2 alpha. So what it means is that the smaller the loss, the higher the Q, okay? And I have this written out in greater detail in the lecture notes, so you wouldn't have this kind of things been messed up here. But what happens then is that Q is defined to be this, and you can also define Q by other ways, by saying that if you have a cavity, then you can say that inside the cavity, the electric field, if it's lossless, the electric field will be proportional to cosine of omega t plus phi, for instance. But if there's some loss, then the electric field would decay as this, okay? And then the magnetic field, similarly, would also decay with this constant, cosine of omega t plus phi 2. Maybe these two are not necessarily in phase. And if the electric field is given to be that, then the energy E squared would decay as e to the minus 2 alpha t. Okay, the energy stored in the magnetic field would decay as e to the minus 2 alpha t. And then what you can see is that the total energy stored, which is usually proportional to the energy stored in the electric field plus the energy stored in the magnetic field, okay, will be proportional to a constant times e to the minus 2 alpha t. Okay, so the energy stored would decay in this manner. Then you can see that the time constant in this case is 1/2 alpha. We can define the time constant to be 1/2 alpha. And then the Q of the system can be thought of as the number of cycles within this time constant, which is omega/2 alpha. Okay, this will be the Q of the system. So the Q of the system is given by omega/2 alpha, which is the same formula that I have derived before. So if you have a cavity with electromagnetic field inside, and if the cavity has some losses on the wall, for instance, if there are dissipations on the wall, as well as if there are dielectric losses in the medium, or if there are holes in the cavity, then this magnetic field and electric field inside would diminish with time according to this manner, and then you can define the Q of the cavity to be such. You can also use energy conservation argument to derive this kind of formula. Okay, you can say that by energy conservation, the power dissipated, time average power dissipated, must be equal to the rate of change of the time average energy stored. Okay, but we just argue ourselves that WT is proportional to W0 e to the minus 2 alpha t. Okay, so which means that ddt of WT must be proportional to minus 2 alpha W0 e to the 2 alpha t. And this means that this is minus 2 alpha WT. Okay, but this has to be equal to, the left-hand side must be equal to minus PD. And you can estimate your alpha would be equal to PD over 2WT. Okay, so if you know the dissipated power and it's time average inside the cavity, then alpha can also be estimated by this formula. Then the Q is given by omega times alpha over omega divided by 2 alpha. Okay, that was a previously derived formula. And then if you plug that in there, you will get the Q is omega WT over PD. Okay, so if there are ways of estimating the total energy stored in the cavity, and if there are ways of estimating the power dissipated in the cavity, you can find the Q of the cavity, which means that if the cavity has a lot of stored energy, but very little power dissipated, its Q is high. Whereas if the power dissipation is high, the Q is low. Okay, and it also says that the higher the frequency, the higher the Q. Okay, so it is a measure of how many cycles you can have before the energy decays to 1 over E of its original value. So if the cavity is oscillating very quickly, you have many cycles before it decays to 1 over E value. So the higher the frequency, the higher the Q value too. Okay, so these are important formulas for Qs. Are there any questions so far as to what a Q of a cavity is? The Q of a cavity is something that is proportional or inversely proportional to the loss of the cavity. And you will see this kind of decay rate in the electromagnetic field. Inside the cavity, you will have this kind of decay rate because of the losses in the cavity. And it is very similar to what you have, say, for instance, in an LC tank circuit. When you have a loss in the tank circuit, then the field, the voltage and the current will decay with time, giving rise to this kind of picture. And the same thing happens inside a cavity. Okay, so let's try to estimate the Q of the cavity next then, if you don't have any questions. Okay, so we want to estimate the Q of the cavity, but before I do that, I'd like to relate the Q to the pole location. So if you have a transfer function y of omega that looks something like what we have previously derived, which is the transfer function for an LC tank circuit. And the transfer function would be something that looks like this. Okay, and that if you were to plot this transfer function, it will look something like this. Okay, it will look something like this, that the transfer function would have a peak right at the resonant frequencies. When these two terms cancel each other, the denominator becomes very small. You will see a peak. However, you can get the peak to be smaller and smaller if you add more resistors. If you add more resistors to the circuit, then you will see that the Q diminishes. Okay, as seen here. Why is that so? You can understand this using a pole analysis, a pole zero analysis, which says that if I were to do a Taylor series expansion of this function, okay, about this resonant frequency, then this function can be approximated by something like this, okay, where the resonant frequency is given to be the case when j omega L plus R plus j omega C equal to 0. When this is equal to 0, then it corresponds to the resonant frequency of the LC tank circuit. And you can see that this can never happen for real omega, okay? No real omega solution. In order for this equation to be satisfied, omega has to be a complex number, which means that the omega sub r that satisfies this equation is complex. Can you see that omega sub r is complex? And hence, if I were to do a Taylor series expansion of the denominator about this value, which makes this go to 0, you will have an approximation something like this. But omega r is always a complex number now. Can everybody see that? You can approximate this function by this, but because the root of this equation is a complex number, your Taylor series expansion would be something that looking like this, where omega sub r is a complex number. Is this clear to everybody? Okay, so I can actually write the transfer function. If omega r is a complex number, say it is omega 0 plus j alpha. Okay, then my transfer function would be approximately equal to a divided by omega r minus omega 0 minus j alpha. Okay, and you can see that omega 0 is the real part of the resonance frequency, and when my operating frequency is equal to omega naught, this thing peaks. Okay, and when it starts to move away from this complex number, it starts to become smaller and smaller, which means that you probably have done something like called Bode plot in your undergraduate days. If you've done something like Bode plots, you can see that this thing peaks when omega equals to omega naught, and then it starts to diminish when omega is larger than omega naught. So if you were to plot this in the complex omega plane, okay, and this is the pole location, omega sub r is equal to omega naught plus j alpha, and then your operating frequency is always on the real axis that you do in Bode plot, and the function, this function will peak when omega equals to omega naught. Okay, and you can do some trigonometry to show yourself that when you are over here, okay, this displacement is alpha. Okay, this distance from the real axis is alpha. You can see that when omega is equal to omega naught plus alpha, and then omega naught minus alpha, then the peak of the signal is 1 over square root of its original value. Okay, you can easily show by using your Bode plot advantage that this distance here is root 2 alpha. Okay, this length here is root 2 alpha when this distance here is alpha. And because of that, you can see that when omega is omega naught plus alpha, then the peak, okay, this peak will diminish to 1 over square root of its peak value. And if you were to square this transfer function, that would be the power. And you can see that the power actually peaks at omega naught, but then it will start to diminish to its half power bandwidth. This is omega naught minus alpha. This point can be here, omega naught plus alpha. And these points here are called the half power bandwidth. The half power bandwidth, and you can define the half power bandwidth to be 2 alpha. Okay, so you can actually get this 2 alpha quite easily by studying the half power bandwidth of an LC tank circuit. You can also get the alpha by studying the half power bandwidth of this thing and then get the Q that way. Okay, so the bandwidth is actually related to the pole location, and the reason why it behaves like that is because you do have a pole that is on the complex plane. Are there any questions regarding this? Okay, then the next thing I like to do is actually to estimate this Q for a cavity. Okay, I like to estimate this Q for a cavity or microwave cavity. Okay, let me put this here. So I'm going to have a microwave cavity. And then I would use this as an example. Okay, and see how we can estimate the Q of the cavity. Let me see. I don't have any more equations there, but what happens is that I'm going to use a perturbation concept. That if I have a cavity, I can find E field inside the cavity, H field inside the cavity in closed form. Okay, we know how to do that in this course. And then I can estimate the wall loss. From closed form solution. How do I do that? Well, this is something using what is called a perturbation concept. First, let's assume that the wall loss is 0. In other words, let's assume that the conductivity is infinitely large. If the conductivity is infinitely large, then there's no wall loss because we have perfect electric conductor on the wall of the cavity. Okay. And then we assume that the conductivity is not infinite. If the conductivity is not infinite, then there will be some wall loss because N cross E is not equal to 0 if sigma is not infinite. Okay. And if N cross E is not equal to 0, the power dissipated by the wall is something that is proportional to half the real part of E cross H. So this is the pointing vector in the cavity. And if I dot it with normal to the cavity wall, that will be the pointing vector flowing with power into the side wall. And then if I integrate this over all the 4 or the 6 walls I have this in this cavity, that will give me the total power dissipated. But how do I estimate this integral? Well, I can estimate it by first assuming that E is very small. E should be 0. If N cross E equal to 0, you can easily see that using the vector identity, I can write this as N cross E dot with H star. Okay, I can, using this identity, that A dot B cross C is equal to C dot A cross B is equal to B dot C cross A. This is the cyclic identity. I can easily use this identity and move the N into the E and crossing with it. And I can see easily that if I have a perfect electric conductor on the cavity wall, this term would be 0 and this term would be 0. But if the cavity wall is not perfect electric conductor, then N cross E would not be 0. And then I can estimate this power that way. But what about H? I'm going to use the perturbation concept that the H is very similar to that of the original cavity. Let's assume that H is very close to the H of the original cavity. But E is not. E goes from 0 to something that's non-zero. H is very similar to the H of a cavity with perfect electric conducting wall. Okay, so how do I estimate E? And I'm going to use a concept that we have learned before. The transmission of an electromagnetic wave at an interface. And if we have an interface such as this, where one medium is highly conductive, the other one is just air, we know that by phase matching, the field has to be refracted in such a manner so that the beta vector is almost normal to the surface, because beta t is omega mu epsilon t, and epsilon t is that of the conductor. It is going to be epsilon minus j sigma over omega, and sigma is going to be very large. Okay, when sigma goes to the infinity, then beta t tends to be very large. So when beta t becomes very large, the only way you can phase match the incident wave with the transmitted wave is for the transmitted vector to be normal to the surface, so that it has almost zero component at this interface, even though it can be very, very long. And if it has almost zero component, then you can match it with the beta that comes in, because the beta on this side is much smaller, and that the tangential component is much smaller. Beta t has to be almost normal to the surface. Because the wave has to be almost normal to the surface, you can estimate the solution in this region with the plane wave. Assuming that it is a plane wave, then what you can do is that you can say that the n cross E is very much like that of a plane wave. So n cross E on the transmitted side would be equal to tangential H. Tangential H is going to be purely tangential because this is a PEC surface. A PEC surface will have magnetic field tangential to it. And it would be that tangential magnetic field times the intrinsic impedance of the metal. Okay, where Zm is the intrinsic impedance of the metal, and we have studied this in homogeneous medium before. But even in the lossy medium, this is true. Okay, we have studied plane wave in lossy medium. And what you have to do then is to replace epsilon with a complex permittivity. And if you plug that in there, then you can see that this would be approximately equal to square root of mu j sigma over omega. And then this would be, if you work out the math, it would be omega mu over 2 sigma 1 plus j. Okay, 1 plus j because, yeah, I think there should be a minus j here, sorry. You have a minus j and then you get the 1 plus j there. So we can let Zm be a very small number because you have a high conductivity. Sigma will be large, so Zm will be a very small number. And tangential E field would not be 0, but a small number proportional to Zm times Ht. You can see that when sigma goes to infinity, n cross E becomes 0. Okay, so you can use this to estimate the tangential E field, and then you can plug into this integral. You can plug into this integral and then compute the Q. Okay, I wouldn't go into the detail because it's done in the lecture note. You plug in this integral, do all the pointing vectors into the 6 surfaces. You can calculate this, and then you can calculate Wt. Wt would be given by the energy stored. Okay, it would be something like half mu h square dv plus half epsilon e squared dv. And that will give you the energy stored in the cavity, and you can work this out by essentially plugging and chugging. And the details are worked out in the lecture notes. I wouldn't work it out. But you will find that the Q of the cavity, the microwave cavity, is proportional to, okay, Wt over Pd with an omega out there. So what happens then is that the numerator is proportional to energy stored in the volume. Okay, the denominator is proportional to power dissipation on the cavity wall. So you will find that this thing is proportional to the volume divided by the surface area times the skin depth. Okay, this is a skin depth, which means that the larger the volume, the higher the Q. So if you can make a cavity where the volume to surface area is very, very large, you get a very high Q. And delta is the skin depth is given by this formula that you have learned before. Okay, if the conductivity of the wall is very large, then delta becomes very small, and then you also have a high Q. Okay, so large cavities in general have very, very high Q. Okay, that's what I want you to learn. And in optics, it is very easy to has high Q. Why is that so? Because you can make an optical cavity very large very easily because the wavelength is very small. As a result, in optics, you can have Qs of a few millions quite easily. Whereas in microwave engineering, in order to get high Q, you will have to make the cavity very large, or you can use superconductors to make sigma very high so that delta becomes very small. Are there any questions regarding the Q of a cavity? Okay. The next thing I'd like to talk about is actually mode orthogonality. Mode orthogonality and how that is related to the matrix eigenvalue problem. This is also called a EVP. Okay, so we have learned about mode orthogonality in other courses, but not in this course. But I like to point out the fact that mode orthogonality of the cavity modes and the waveguide modes are very much related to the matrix eigenvalue problem. Okay, so let's assume that we have a matrix eigenvalue problem such as this one. Okay, and then if we find two different eigenvectors, like A dot Bj is equal to lambda j Bj. Okay, you can easily convince yourself that if I were to multiply this equation by Vj conjugate transpose, and then multiply the second equation by Vi conjugate transpose. Okay, and you can see that the left-hand side, they're actually equal to each other. If A is Hermitian, which means that A conjugate transpose equals to A. You can see that the left-hand side is very exactly equal to each other because left-hand side is a scalar number. And if it's a scalar number, then if you take its conjugate transpose, it should be Vi conjugate transpose dot A conjugate transpose dot Bj. Okay, if I just take the conjugate transpose of this, okay, this should be a J. And then when you subtract these two equations, you will end up with the fact that as is often shown in matrix eigenvalue problem, you get 0 on the left-hand side, lambda I minus lambda j, Vj conjugate transpose Bi must be equal to 0. And hence, when lambda I is not equal to lambda j, we must have these two eigenvectors equal to 0. Okay, or in general, you can say that the right-hand side should be a Kronecker delta function times C, which means that different eigenvectors are orthogonal to each other. And what we have actually is the fact that when we are solving Maxwell's equations and looking for the eigenfunctions of the cavity mode, we are essentially solving for the fact that we are looking for eigenvectors of a more abstract operators. I can start with, say, looking at the waveguide problem first. And for the waveguide problem, we say that we have a reduced wave equation that we solve. And that reduced wave equation looks something like this. And we say that this is the eigenvalue. Okay, and we can think of this as being equivalent to my matrix operator. Okay, matrix operator. And if I think of this being the matrix operator, I can look at this as actually being analogous to this equation. Okay, these two equations are actually analogous to each other, which means that I can think of this as being analogous to this, and that being analogous to that, and then lambda sub I being analogous to that. And with this knowledge, you can easily prove that the modes of a waveguide are orthogonal to each other. Okay, so you just have to think of the Laplacian operator as being a linear operator of some sort. You can think of this transverse Laplacian operator that when it operates on a function R sub S, it actually produces a new function. Okay, so this thing is very much analogous to a matrix times a vector is equal to a new vector. Okay. So a Laplacian operator, the two-dimensional Laplacian operator is actually analogous to a matrix operator. And you can prove that this is Hermitian. Because it is Hermitian, you can prove that the eigenvalues that it has, which are these things here, would make all the functions to be orthogonal to each other. And I have written this out in greater detail in the lecture notes, but the proof is rather long. I wouldn't go through the proof here, but I just want to let you know about this abstract concept. The abstract concept that when you have a Laplacian operator, it is analogous to a matrix operator, except that this is an operator in an infinite dimensional space, and that is usually called a Hilbert space. Whereas if you have taken a course in linear algebra, this A is a matrix operator in a finite dimensional space. This is a vector. I can think of any function as a vector. Okay, where I would have, if I were to represent this function with discrete values in the space, then it would be very much like that. Each component of this function vector is its value at the location R sub I. And again, I can break this vector into its components. Each component is X sub I. Hence, I can think of a function. It's a vector. Okay, function is a vector. So when you can think of a function as a vector, you can think of this being entirely analogous to this thing that we have. This is a vector. This is the matrix operator. This is just the new function that it produces. Okay, then you can actually understand mode orthogonality. You can understand mode orthogonality inside a waveguide, and you can see that when you have a cavity problem, you can also solve it using the scalar potential approach. Okay, then we have actually the scalar pilot potential should satisfy this equation, but sorry, this in the 3D problem, this would be that. And then you can see that this problem can also be written as minus beta square size of R, where beta square in the case of the rectangular cavity is n pi over a square plus n pi over b square plus p pi over d square. Okay, so these are discrete values. And again, I can say that this is very much analogous to this problem. Okay, and hence all the modes of the rectangular cavities should also be orthogonal to each other because of this reason. For the same reason that eigenvectors of a matrix operator are orthogonal to each other. I'll stop here and ask you if you have any questions. Any questions, anybody? Okay, if there are no questions, I'll let you go. Okay, thank you for coming. And I think there should be an office hour tonight if you're interested in attending office hours. Okay, thank you for coming.